Well, welcome to the last Science Center review session for your exam on electrochemistry. My name is Jessica, and I'm a PLTL leader for Chem 1312. And my partner here can introduce himself too.
Hello, I'm Prashant, and I'm a peer tutor for Chem 1312.
So we're going to be your leaders for today, and today's topic is just electrochemistry. The review, just like it usually does. So me and him will be covering the material first, and then you'll have leaders in the chat answering your questions. And then we're going to move on to breakout rooms where you guys will get to work some problems. So I guess without further ado, we'll get started on the material. So the first thing we have is some redox review. So redox stands for reduction and oxidation. And reduction means the gain of electrons because we know electrons are negatively charged. So when we gain them, we get to a smaller number. And then oxidation means the loss of electrons. Make sure you keep this in mind when we're doing galvanic cells and everything like that. There'll definitely be questions on which one's being oxidized, which one's being reduced for that. And some rules to keep in mind. I put an arrow beside the bigger rules, I would say, but there are some extra ones here that may come up. So just remember that elements in their individual states, which also includes diatoms, will add up to 0. Then when they're ions, they'll add up to their charge. Hydrogen in compounds will have a +1 charge most of the time. And you can see rule 4 shows an exception where hydrogen might have a different charge. Oxygen will most likely have a -2 charge. And again, rule 6 shows an exception where oxygen might have a different charge. But again, hydrogen and oxygen more than likely will go with their regular +1 and -2 charge, respectively. Very rarely do they put exceptions to those. And then group 1 elements, you can expect them to have a +1 charge. Group 2 elements, you can expect them to have a +2 charge. And then halogens, most of the time, will have a -1 charge. Halogens, you'll see more exceptions to, so just keep that in mind. Halogen will always have a -1 charge. And then the sum of oxidation numbers in a compound without charge is going to be 0. But then when the compound is a polyatomic ion, so that means that compound has a charge, it's going to equal the charge. And so make sure you know these rules. You probably won't be asked about redox reactions too directly, like you were when you initially learned it in Gen Chem 1. But it'll be more application based. I would just review these just in case though, especially since you might have to look at like those line notations and figure out which one's being reduced, which one's being oxidated, and all that stuff. And so here's an example of a reduction and oxidation in a reaction. Remember, redox reactions happen together because the reduction allows for the oxidation to occur. So you won't see a reduction and a reduction in one reaction. It's always going to be a reduction and then an oxidation. So if you're given to reduction half reactions, keep in mind that one is going to end up being oxidized. So you're going to have to flip one when you're writing out the whole final reaction. And over here, we can see that iron is being reduced because it goes from a +3 charge to a 0 charge. And then carbon over here goes from a +2 charge to a +4 charge. So it's being oxidized. So yeah, keep this in mind, or we'll go back and review if you're finding some of the redox stuff rusty. So how you'll be asked about it more likely is their half reactions in acidic and basic solutions. So they're slightly different. I would say the acidic solution half reaction balancing is a little simpler. So you're going to start with balancing your non-oxygen and hydrogen atoms. So in this case, you see they balance the iron and then they balance the chromium. Next, you're going to go on and balance your oxygen. So in the case of iron, we don't have any oxygen, but in the case of the second reduction half reaction, we have some oxygen, so we have to add water to balance it, H2O. But then adding H2O also adds in hydrogen. So now we also have to balance the hydrogens. And so you're going to add H plus to balance hydrogen. But adding this H plus also changes the charge, so keep that in mind, and then balance the charges by adding electrons last. You kind of want to stick to this order, because if you try to balance the charges before you add the H plus, you're going to find that your charges have changed, and you can't really balance the H plus until you add the water, because H2O changes the amount of hydrogens you have. So yeah, this is kind of like the steps you want to take in the order you want to go through. And then when you get your individual half reactions balanced, you want to eventually combine them into a total balanced full reaction. So make sure when we're doing a full reaction, your electrons cancel. We don't ever want those electrons to remain there. So you can see that iron initially didn't have a coefficient, but because when we balanced the chromium reduction half reaction, then we had 6 electrons. We had to multiply the oxidation half reaction by 6 so that we can get the electrons to cancel. And you can see the electrons always have to end up on the opposite sides as well for the canceling to work out, or else they'll add. So you do the multiplication and cancel out the electrons, and then you'll have your full balanced reaction. And so balancing half reactions in basic solutions is quite similar as well. Some of the longer, as you might see by this example. So you're going to start with the same steps. You're going to balance your non-oxygen and hydrogen atoms. Then you're going to add H2O to balance oxygen. You're going to add H plus to balance the hydrogen. Then you're going to balance charges by adding electrons. And then for 5, you add equal amounts of OH minus on both sides to form water out of the H plus atoms. Because in the end, you want those hydroxide atoms in solution. Because we're dealing with a basic solution, right? So if we have H plus atoms, that's acidic. So that's why we add equal amounts to both sides. So we're not changing the amounts of oxygen and hydrogen, but we're still making it an overall basic solution. And keep in mind that step 4 and 5 can happen interchangeably. So sometimes people like to balance the charges after step 5. You can do that because we're adding the same amounts of hydroxide. So if you're adding equal amounts to both sides, it shouldn't really change the charge composition. And then you want to also keep in mind that simplification, usually you need to do that because, again, when we're adding the hydroxides, in order to cancel out the H pluses, we want to actually do that and make them waters, right? So you can see going from step 4 to step 5, the 12H plus and the 12OH minus combine to make 12H2O. But then now we also have H2O on the other side. We have 6H2O. So having the same thing on both sides means we can reduce the H2O, so we only have 6H2O on the right side. So you want to keep that in mind, because if they're doing something like this on the exam when it's multiple choice, they'll probably give you the fully simplified version. So if you forget to simplify, you might not see your answer choice there. Yeah, and again, you want to make sure your electrons cancel on both sides when we're combining it. So in this problem, it's only a half reaction, so we don't see the combination. But if there's another half reaction, we would combine it, make sure those electrons cancel out, and we'd have a full balanced reaction. Also, don't forget that when we're balancing, you have to split it into the half reactions. You can't do it as a one big reaction. Okay, so those are the differences between the basic and the acidic ones. Make sure you read carefully on which one you're doing it in. And then these redox reactions allow for the conversion of chemical energy into electricity when we're talking about stuff like galvanic cells, right? We're harnessing the reduction that happens at the cathode, the oxidation that happens at the anode, and we have the cyclical conversion of energy And yeah, redox reactions allow that to happen. So that's why they're important, and that's why we learn about those.
All right, so to start talking about galvanic cells, it's important to know the components of what makes up the cell. So for every galvanic cell and the other cells we're going to be going over, you're going to have an anode and a cathode. So the anode is always where oxidation is going to occur. So oxidation occurs because the anode, whatever the metal is that the anode loses electrons, thus leaving Zn2 plus into the solution, as in this example, and then the electrons are able to travel through a wire to our cathode. So the cathode is where reduction happens. So the electrons from the anode travel through a wire to the cathode, thus reducing the cathode. So the important concepts to know with this is that your anode will be considered your negative terminal, while your cathode is considered your positive terminal. Also, it's important to know that there's going to be a salt bridge that connects both cells. So the purpose of the salt bridge is because whenever Zn in this example at the anode loses electrons, that means the anode starts becoming more of a positive charge because it's losing electrons. So in order to balance that out, we put a salt in a salt bridge, and then the anion goes towards the anode to like balance out the charge, while the cation goes to the cathode to balance out the charge over there, thus allowing for the cells to like continue to function in that way. And then the other important thing you need to know about galvanic cells is that your E0, so your potential of your cell at standard conditions, is going to be greater than 0, which means that your delta G is going to be less than 0. So galvanic cells, this process we're going over happens spontaneously. So here's the example we had in the previous picture. We had zinc as our anode. So as you can see, it's losing 2 electrons to form Zn2 plus so that's oxidation. And then our copper was our cathode. So the Cu2 plus in the solution in the cathode cell would be getting electrons added to it, thus forming the copper solid. So an important notation you'll need to know is this bar notation, which basically shows you like the reaction happening in a cell. So the first thing that's shown will be your anode, and it'll show you what it's oxidized to. And then you'll have your cathode on the opposite end, and you'll have the 2 ions in the middle. So being able to understand these like notation and know what reaction is occurring will be important for your test. And now to go into standard reduction potentials. So the definition of standard reduction potential is just the potential associated with a reduction half reaction at an electrode when the ion concentration is 1 molar and the gas pressure is 1 atm, which essentially means that at standard conditions, this is like the potential that will be reduced at. So these reduction potentials provide us with 2 important things. So the first thing is whenever you're comparing 2 reduction potentials between 2 different reactions, the more positive reduction potential will be the one happening at your cathode, and the more negative or the smaller one will be the reaction happening at your anode. And then in addition, the second thing is that your reduction potentials allow you to find your E cell at standard conditions. So to find E cell at standard conditions, you need to take your reduction potential at your cathode and then subtract by the reduction potential at your anode, and that allows us to find our E of the cell under standard conditions. So why is that important? This is where we get to connect this to some past units. So we know that for spontaneity, we know that delta G needs to be less than 0 for spontaneous reactions, and delta G is greater than 0. So as you can see from this expression, that delta G is equal to negative NFE, where E and G are both under standard conditions. We're able to see a relation. So when E is positive, our G will be negative, and vice versa. So in this expression, we have that N, which is going to be the moles of electrons transferred, and we're going to have F, which is our Faraday's constant. So I wrote down Faraday's constant as 96,485 coulombs per mole of electron. You could get a rounded value on your test, so like you might get 96,500. I'm not sure what which value you guys will need to use, but it's around this value. Another important thing to know is that you can write coulombs per mole of electron as joules divided by volts times moles of electron. So that's just another way to write the unit. but it's still the same value. So now we can relate our E cell under standard conditions to our K. So from our previous chapters, we know that delta G under standard conditions is equal to the negative RT times natural log of your equilibrium constant K. And we learned in this chapter that our delta G0 is equal to negative NF times our E0 cell. So what we can do is set those two values equal to each other. And that allows us to get this formula where our E cell under standard conditions is equal to RT, where R is our gas constant times our time. And we divide that by, I mean, not our gas constant, my bad, our energy constant. And we divide by our moles of electrons transferred times the Faraday's constant, and that times the natural log of K. So we're able to relate those two equations to get this. And now what happens if we're not in standard conditions? So our delta G under non-standard conditions is equal to negative NFE still, but our E cell is not under standard conditions. So using some knowledge from our last units, we know that delta G is equal to delta G0 plus RT ln of Q. And now we can substitute our delta G for negative NFE cell. And we can substitute our delta G under standard conditions using our negative NFE cell under standard conditions. And now if we divide by negative NF, we finally get to our other equation, which is that our E of our cell is equal to the E of our cell under standard conditions minus RT divided by NF ln of Q. So here's just a summary of the equations if you just want kind of a list of which equations you'll need to know. So, and then here's a nice little chart which relates delta G, E, and K under standard conditions. So we have our equations that go from delta G to E, and then we have our E to K equation, and then our delta G related to K. So as you can see, all three are related. And then the other important concept is the signs. So if our delta, depending on the sign of our E, we need to be able to tell what our sign of our delta G is. So basically E and delta G have opposite signs. So if E is positive, delta G is less than 0. And then in that case, K is greater than 1. And then if delta G is greater than 0, we know that our E is less than 0 and K is less than 1. And then at equilibrium, we know that delta G is equal to 0, which means our E cell is equal to 0, which means our K is 1. So knowing the relationships between the signs will be important. And now to go into our second type of cells, which are concentration cells. So in these cells, we have two different half cell solutions, and they only differ in the concentration of ions in that solution. So in our example here, we have a zinc 2+ that has 1.0 molar concentration, and another one that's 0.1 molar concentration. So for these cells, your anode and cathode are still the same concept. So your anode is going to be the one that's oxidized, your cathode is going to be the one that's reduced. In addition, like galvanic cells, your anode is going to be your negative terminal, and your cathode is going to be your positive terminal. But one of the important things you need to know about concentration cells is that your cathode is going to be your cell with a greater concentration. So what that means is in this case, our Zn2+ at 1.0 molar concentration is greater than our 0.10. So our Zn2+ is getting reduced to Zn solid, so thus being our cathode. So in our anode is the one that gets oxidized to our lower concentration. So the second important thing you need to know is that your E cell at standard conditions for any concentration cell is 0. So it's going to be 0. And then if we plug that into our E expression that we got before, we can plug in 0 for E0 cell. And then for our Q value, we can just use our equilibrium constant writing rule, or like our reaction quotient writing rule. So we do our products divided by our reactants. So as you can see, because our cathode is the one with greater concentration, whenever we do products divided by reactants, we'll get our dilute ion concentration. So in this case, 0.1, and we would divide it by our concentrated ion solution. And we'll get roughly an equation that's going to be like E equal to 0 minus RT ln, RT divided by NF times the natural log of your dilute concentration divided by your concentrated ion concentration. So here's just a little image. As you can still see, there's still a salt bridge between the two. Our cathode is positive, our anode's the negative terminal. And our anode is the lower concentration, while our cathode has the greater concentration of Zn2+. So finally, our last type of cells that you'll need to know for this test is electrolytic cells. So in these cells, it's still the same anode is oxidized, the cathode is reduced. So the important thing with this cell, though, is that your E cell is less than 0, which means that your delta G would be greater than 0. So we know that delta G greater than 0 means that the reaction does not occur spontaneously. So we need something that will allow the reaction to occur, because it's not going to occur naturally. So that's where our battery comes into play. This allows us, the battery provides the potential that's needed to do a non-spontaneous reaction. So the important thing in this case is that, unlike your previous two cells, your anode in this case is the positive terminal, while in your galvanic cells it was the negative. So in the electrolytic, that makes your cathode the negative terminal. So this is split from the previous two cells that we just went over. So knowing that distinction will be an important concept to know. And then finally, you'll know that you're dealing with an electrolytic cell if you see the word molten. So if you see the word molten in your question, you can assume that you're most likely dealing with an electrolytic cell and doing an electrolysis problem. So yeah, so we're to compare galvanic versus electrolytic, as we went over, our anodes and cathodes have different terminals. So in the galvanic, your anode's the negative terminal, but in the electrolytic, your anode is the positive terminal. Second, as we went over, your galvanic does spontaneous reactions, so delta G less than 0. And your electrolytic does non-spontaneous, which means that your delta G is greater than 0 for these cells. And which means that because our delta G is greater than 0, we need an external voltage source for our electrolytic cell, aka a battery, while we don't need one for our galvanic cells. And finally, to get into the math of electrolysis, so most of the math involving these types of cells are going to be basically dimensional analysis problems. So the first thing you want to keep in mind is that your unit of current, which is amps, which is written as the letter A, is the same unit as your coulombs divided by your seconds. So those are the same. So your 1 amp is equal to 1 coulomb divided by a second. So this is going to be important for a lot of problems. So whenever you see your amps, it'll be important to write it as coulombs divided by second. And then you just work through dimensional analysis from there. So I gave a few examples of like kind of the thought process you'll go through. So if you're like trying to solve for time and we have a reaction that we know how many moles of electrons are transferred, we can use our coulombs constant to cancel out moles of electrons. And then to cancel out coulombs, we use our current that would have been given in our problem. And that just leaves us with seconds. So through dimensional analysis, we were able to solve for our time aspect in this case. So if in another common case you're definitely going to get is to solve for a gram of some compound, which I just called X in this example. So to be able to get there, you can again use dimensional analysis. So if you start off with a current you're given in the problem, and you convert it to coulombs divided by second, because those are the same units, and then you're going to be given a time in the problem. So in these types of problems, it'll be important to have your time in seconds. So you're most likely going to have to convert hours or minutes into seconds. So this allows us to cancel out the seconds. And then anytime you want to get rid of coulombs, you're most likely going to have to use Faraday's constant. So that's where Faraday's constant comes into play to get rid of coulombs. And then to get rid of moles of electrons, you need to know your reaction. So if your reaction involves zinc, you know that zinc, whenever Zn2+ gets reduced by 2 electrons to get to Zn solid. So you can set up a molar ratio between the moles of electrons and the solid that's being formed. So knowing your half reaction in that case is super important to come up with this molar ratio. And then finally, once we get our moles of our compound, we can just use our molar mass to get to our grams. So as you can see in both of these examples, we're able to use dimensional analysis to get to our final unit. And then you can just plug in the numbers into your calculator and get your answer.
Here they come.
So we're in the main room. So our session is going to be recorded, just to let you guys know. And I believe that includes the messages in the chat. So yeah, just want to put it out there. This is going to be on the YouTube as well. So let's get started. So problem 1, which is our longest problem, has 4 parts. Galvanic cell is made using aluminum as one of the electrodes, just the other electrode. Standard reduction potentials are given below, so the table we're using for this problem. Identify which electrode is the anode and which electrode is the cathode. Any ideas how we can do this? Yeah, exactly, right? Because we're working with a galvanic cell, and we know galvanic cells have a spontaneous reaction. So we want our overall E cell to be positive, right? Since that will correlate with spontaneous reaction. So let's see, which one would that be then? Aluminum for the cathode or zinc? We have to look at these numbers over here. So aluminum is right over here, and then zinc is over here. So we can find it. So we're saying zinc is the cathode? With you? This is aluminum, right? Okay, cool. So let's label that just so we have it down. So zinc is the cathode. I'm going to just put it on top of the word. And then the anode would therefore be aluminum. Now we're going to write out the balanced chemical equation for the reaction that takes place. So we know if zinc is at the cathode, is that a reduction or oxidation? Yeah, it's going to be the reduction. So I'm going to write the thing straight from the table, right? Because the table has the reduction potential. So that's our zinc. And then if our aluminum is the anode, are we going to write it as the reduction in the table or do we change it? Yeah, we're going to have to do the oxidation. How does that change it? Flip, exactly. Is that all we have to do though? We're going to write it balanced. A full balanced reaction. Can we just combine them? Yeah, we have to balance the charges, right? Because if we combine them right now, the electrons won't cancel. And balanced final can't have them not cancel. So you're exactly right. Multiply 3 for zinc. And multiply 2 for aluminum to end up with 6 electrons for them. So once we do that, we'll have 3 zinc 2 plus 6 electrons plus 2 aluminum solid. And then that yields 2 aluminum 3 plus 6 electrons again plus 3 zinc solid. So to finally end this off, okay, I'm going to move this over here because it was going off the page. We're going to cancel out those electrons. So you see how they're on opposite sides because we want the oxidation to be in the correct format. And then once we cancel the electrons, we have the full balanced reaction. Any questions so far? Cool. So C is calculating the E cell. Anyone remember how to do that? Anyone? I'm going to do cathode minus anode when we're doing the E cell in that format. The thing is, there are 2 strategies you could really take. Is you can do the straight formula version, or you can remember that you're flipping it and change the sign. You get the same answer no matter what you're doing. So if we're straight up flipping it, we know at the cathode, if we're doing the formula, I mean, first we're going to do the formula version. So the cathode we said was zinc, right? So it's going to be negative 0.76 minus negative 1.66. You can write it that way, or you can write it the way where we know that since the reduction is going to be zinc, and then the oxidation is aluminum, we can add them, but we have to make sure we flip the sign. Either way, you end up with the same answer. Negative minus and minus negative would give us that positive anyway, right? So however you think of it, still come up to the same answer. Just make sure you're working with either or. You're not like mixing them. So what do we get for that answer once we do the math? What is the value? Yeah, 0.9. What's the units for this? Volts, exactly. Everyone get what I'm saying about the formulas and like the other option where you could just like think of it as a plus if you flip the oxidation sign? Okay, cool. And lastly, it says to find delta G. So we're going to find the Gibbs free energy of the galvanic cell. And we're going to use this Faraday's conversion factor. So remember, just use the one they give you on the exam because like he said, they might have it rounded a little differently. This is the one we're going to use. Anyone remember the formula we're working with? Negative NFE. So and you guys know what N stands for? Yeah, it's going to be moles of electrons. What in this problem? That's going to be 6. So you see, that's also a reason why we have to balance it, right? If we look at zinc on its own, we can see 2 electrons. Aluminum on its own has 3 electrons. With a balanced one, they both have 6. So make sure we're balancing so we could also find that out. Now Faraday's, they give us, so 9, 6, 4, 8, 5. And then lastly, we found our E cell to be 0.9 volts. So when we do the math on this, you should negative 521. Want to know the units? Yeah, in this case it's kilojoules. You might have, if you do the math, you could see that it was converted. But keep in mind that the Faraday's constant has rules in it. So be careful, know your constant units so that you don't mix them up. Okay, any questions on this problem before we move on? No? Okay, cool. The symbol cancels out. Yes, I think you're right by that. I mean, sometimes I still write it in. I think mole is one of those things where like it's sometimes written and sometimes not. If you like look at like tables where they give you values, yeah, I don't think it's that important. I think it may cancel that, but sometimes it is still written in. Yeah, I don't know why they still do it sometimes. I think either or though is fine. Okay. So this is just the solution. So if you see, it just talks through everything we talked through. And this will be on the recording. So if you want to look at the solution in depth, you could just like pause the recording at this point. But since we, I think, agreed on everything, I'm going to just skip. Okay, so problem 2. Problem 2 states a galvanic cell consists of Ag plus at the cathode. And then this zinc 2 plus at the anode. So we're now calculating K. Idea what formula we're going to be using to do this? Yeah, RT over NF ln K, exactly. Equals to E cell. So we're going to start with finding our E cell and then plugging it into that formula. RT and F ln K. Keep in mind, temperature has to be in Kelvin. I feel like that's like one of those easily mistakes, since they often give it to you in Celsius, but because of our constant, we have to convert to Kelvin, or else it will match with the constant unit. Okay, so let's start with finding our E cell. So we know where our cathode and anode is, so we don't have to determine that. We just have to look at the table and use E cathode minus E anode formula. Okay, so our cathode is the silver. Where is that on this table? Okay. This 0.8. That's a positive number. 0.80 minus, and we're looking for zinc now. Over here. Also, we know this is a standard potential reduction potential. Like it's a standard E cell, since they're giving us this table and they don't tell us otherwise. So it's kind of assumed that we're working with the standard values. So this is minus 0.76. And we do the math on that. Any idea what we get? Maybe 1.56, exactly. So now we have to fill in the rest of the stuff to calculate K. So anyone know what the R constant is? Yeah, exactly, 8.314. You don't have to have it memorized, but it does help. Wow, even the units. Good for you. I'm impressed. And what about the temperature in Kelvin? 298, exactly. And N in this case? Yeah, it's going to end up being 2 because that silver only have 1 electron at first, and then the zinc is going to have 2 electrons, so we just multiply that silver, so we get 2 electrons and it'll cancel. So 2 times F, which is the Faraday's constant, so 96.485 times ln K. So everything now is set up, so all you would have to do is isolate the ln K, and then to get rid of the ln, remember that you're raising it to the E, because the opposite of natural log is E, like raised exponential of E. You guys get what I'm saying? I don't know if I'm saying that very clearly. So basically, you would do this math and then divide it over. And then when we want to get rid of that ln, we raise it. We do E to the ln because then it cancels. And then we do E raised to the number we get after all that. Would we use 298.15? Oh, do you mean for the Kelvin conversion? I think it probably doesn't matter. Like, I don't think it'll change your answer drastically. I think to your professors usually tell you what they want the conversion to be. Usually, I just go with the plus 273 conversion? Do your professors ever tell you like it has to be the 273.15 conversion, like on your exams, or do they like I don't know? Like I feel like whatever you guys have been doing so far. Okay, cool. Then I guess I would go with what your professors say because yeah, I don't know exactly what they want from you. Yeah, they don't really tell us. We don't get to make the exams or see the exams. We just do this stuff. But I'm glad your professor will tell you because that sounds helpful. Overall, when we do all this math, though, you're just gonna get A equals let me see, 5.86 times 10 raised to the 52 power. So huge number, huge, huge, huge. What does this K mean? Like in like in like the context of this problem, what does a big K mean? Yeah, exactly. Yeah, and you see a lot of K being associated with a very, 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 very spontaneous reaction, which makes sense because galvanic cells have to be spontaneous, right? So it's and so if you get a really big K whenever you're doing this exam, like that makes a lot of sense. Where you should be concerned is if your K is really small, you might have like done some kind of calculation error. So keep in mind that you probably will see big Ks just to like check your work whenever you're going to the exam. Any questions on this problem before we move on? Okay, cool. And this is the solution. So everything we talked about. Yeah. Okay, let's see. Predict whether the following reaction will occur spontaneously at 298 Kelvin. And these are the concentrations. So what does this mean that the fact that we have the given concentrations? Yeah, it is the Nernst equation. It tells us that we're looking for an E cell, not an E cell at standard conditions, right? Since at standard conditions, we have 1 mole of everything, or 1 molarity of a concentration for everything, right? And so, anyone know the Nernst equation? Any ideas? There you go, yeah. I just wrote as standard, but yeah, same idea. Okay, so very similar to our last problem. So again, we have to find the E cell at standard conditions first. And this table is kind of small. Let's see. So which one is our reduction, cobalt or iron? Yeah, this is going to be at our cathode. And I like to label it so I know what I'm putting it, like when I'm putting it into the equation, I'm putting it in correctly. At least one of them. So let's find our cathode. Iron is over here. Also keep in mind, sometimes there are 2 irons because sometimes they'll give you Fe3 plus and Fe2 plus. So be aware, like check your like little charges. So you accidentally use the wrong 44. Okay. And now what's the anode? It would be cobalt. So what's the number for that? I can't see it on the table. There we go. Found it. So then this is going to be minus 0.28. So what do we have in the end? What's the final value for the standard ESO? Yeah, very good. Okay, so we found that, so negative 0.16 goes in for our standard. So now we get to plug in our other stuff. So this time they gave us the temperature in Kelvin. Sometimes they will, sometimes they won't. Just be on the lookout for that. 298. And N would be 96.485. What's N in this case? Yeah, it's going to be 2 again because both cobalt and iron don't even need to be balanced. They both have 2 electrons. And then LNQ. You guys know how to find Q? Yeah, it's going to be products over reactants. So going back to the equilibrium chapter. You guys know why we don't include, we only include the ions in this problem when we're doing products over reactants? Exactly, yeah. So there's a reason because cobalt solid and Fe solid, they're solids, right? We don't include solids in our equilibrium. So to keep that in mind, 0.15 over 0.6. Let me check. Yeah, that's what I got. So once you put everything into your calculator, you should get Caleb got, which is negative 0.14. And if you actually look, it's super close to your standard ESO. And I find that it's almost always like that. Like your numbers are going to change a little bit, but they're not going to change a lot. Yeah, it's not spontaneous, right? A negative ESO means non-spontaneous. Non-spontaneous reaction. Exactly. Any questions about this one? Cool. Great job, guys. You seem to know everything really well. So here's our key. Everything we did is covered here, so we're good. So problem 4, do you guys know what this type of writing, like the style is called? Like what is this called? Yeah, it's line notation, exactly. So which side is the oxidation side and which one is the reduction side? Yeah, so I was anode then cathode. Exactly. So it's going to be oxidation side as well. So anode slash oxidation first and then cathode slash reduction side. And I always written this way, like that's just proper line notation. Now, so if they have like, I don't know if you guys have free responses on your exam, but if they do and they have like a regular line notation format thing, make sure it's always anode slash oxidation that goes first. And then you have one that splits it up for just the two sides of the oxidation. Then you have 2 bars when it comes between the anode and then the cathode component. It's EMF voltage. I think so. I don't know. Do you guys use EMF here? Electromagnetic force or something, EMF? I remember that in physics. I don't remember that in chem. Okay, cool. Gotcha. Well, I think everyone agrees that it's voltage, so we're cool. Any ideas how to do this problem? formula we're using? So a concentration cell at standard is standard E cell. I think it's EMF. It doesn't say standard in this problem. It doesn't say standard EMF. So what we're at standard? Oh, so same as the last one, but the ln of Q is dilute in standard concentration. Exactly. So it would be the next equation, same idea as that one. Minus RT over NF ln dilute over concentrated. So the answer was not when I did it. Let's see if we could check it out. I noticed they give us a temperature in this one. I think we assumed 298. I think they should tell you on your exam. I think when my partner graded this question, he might have just forgot to tell us the temperature. But on our key, he did assume that it was 298. So we're going to go with 298. They should give it to you in the exam. I don't think they'll make you assume it. And then 0 right over here. And then N is 96,485. 185. And then, or not N, F. What's N in this case? Yeah, it's also 2. 2 is a very common. And then ln dilute. So ln would be, dilute would be 0.24 over 0.53. Let me recalculate what our key has and see if it's right. Did anyone else do the calculation? You got 0.0102? Okay, our key has a different number, but it might just be a key error. So let me just recalculate and see if I get the same thing. It's probably what you guys got because we wrote. I agree with how we wrote it, and it's actually written this way in our thing. Let me check. 8.8. We're going with 0.2 divided by 0.53. Yeah, I agree with you guys. I got the same answer, so I think it's just here. So you see, we got a different thing here, but it's set the same way. So here, we'll just act it for. This is what the answer should be if you're watching it online. Cool. Also, I think Neha, it should be positive. Don't forget that you have a negative because we do have 0 minus the RT and F, L, and Q. And then the L just turns out to like make it a balance, to be back to positive. Any questions about this problem? So problem 5, we got a, let me see, where am I? Problem 5. We got a copper metal weighing this, or that's the mass, is purified by electrolysis. How much copper metal in grams could be produced from copper 2 oxide by applying a current of 10 amps at the appropriate negative potential for 12 hours? So it's an electrolysis metal plating question. So he showed you some math for that at the very end. And this time we're looking write in grams. Often they'll have it like you're going to like the time, the difference like in grams. So any idea how we might start this problem? Yeah, we can write this. So copper metal purified by electrolysis. That's okay. It's late. It was sunny when we started, and now it's so dark in my room. Because I have a lamp. How much copper metal could be produced from copper oxide? So we're saying we have copper 2. We could write this out, but we don't actually have to for the purposes of this problem, unless I guess to look at how many electrons we need. So I guess we could do that, just to find our electrons. So copper 2 oxide, we would say do this. Let me see. Yes, Caleb, you are correct. But I'm going to still go through the problem. Copper solid. Okay, so really we could balance this out. So the coppers, well, we first want to balance that. We had only 1 on that right side. Then we're going to add our H2O. We're going to add our H plus. Two of those. And lastly, we're going to balance out for electrons. So we're going to do 2 electrons. Balance out for charge by adding 2 electrons. Any questions about this balancing? How it's done? We have actually practiced problems with balancing towards the end too. But any questions so far on how I balance this? No? Well, the reason we want to is, I guess, to electrons we need, since that does come up in our math. So how I would start this problem is, given that we have 10 amps, so 10 amps is equal to 10 coulombs per second. So 10 amps equals yeah, I could do that. I'm not sure if it'll work in every single situation though, because this problem is a little different because you're going from copper to oxide. So technically, like it works out for this problem, but I'm not sure it'll work out for every single problem because remember, adding the H pluses changes stuff. So it's not necessarily going to always be the same, is what I would say to that. I'm not 100%. I haven't done enough practice problems to know, like, yeah, if it'll always work. So just be careful with that because it's a different reaction. It's like a different, half reaction. So 10 amps is equal to 10 coulombs per second, okay? So I'm going to start over there. So 10 coulombs. Let me do my dimensional analysis table. Per 1 second. I know that there are 3,600 seconds in 1 hour. If you don't know that, you could convert first to minutes and then to hours. But if you do, it saves a step. And then it tells us we're doing this for 12 hours, right? Okay. And we know that way we can get rid of the seconds. We could get rid of the hour. So we actually don't have a unit anymore for time because everything cancels out that way. So next we have to deal with the coulombs. We want to get those coulombs to what? Grams, right? So that's the last unit we have to figure out. So we know for coulombs, we have 96,485 coulombs and 1 electrons, right? So I'm going to put that all up here. 1 mole electrons. So now we know we have 2 moles of electrons for every 1 mole of copper, 2 oxide. Is that what we're saying? Oh, my bad. Did not mean to write over that. Okay, cool. Okay, and this is going off the page, so I'm gonna actually draw an arrow and do it up there. So I guess for this problem, how much copper metal could be produced from copper 2 oxide by applying? Oh, I see. I think I see what I'm doing. Okay, so copper 2 oxide. So copper 2 oxide, right? If we write that out, if we're saying that copper has a 2 plus charge, we know oxygen has a 2 minus charge. So I actually wrote that wrong, right? Written out, it would actually cancel, right? So as copper oxide, I think. You guys get what I'm saying? Because copper 2 plus and oxygen 2 minus written out would just be copper oxide 2 oxide. I think so. I think that's where I went wrong. Because look at the key. I think that's probably takes into account because you still have two electrons in that case because you still have to add 2 H2Os, and therefore you would still have 2 H pluses, and you still have that. So yeah, I think that's what I messed up. I wrote the 2, but it's copper 2 plus and oxygen 2 minus. They crisscross, and you just get copper oxide, right? Okay, sorry about that. Thanks for catching that. Okay, so I'm gonna write an arrow actually up here because I'm running out of page space. But this goes under the mole copper, right? So we're gonna say that 1 mole of copper, so we cancel out that mole of copper, and then we're gonna use that molar mass finally to convert it to grams. So that molar mass would be 63.546 grams. Sorry, the work is a little messy. So yeah, the 1 mole over here that I'm doing would be right at the bottom over here, just to explain. And this would be at the top. You guys get what I'm showing? I'm sorry, it kind of got messy over there. Okay, so once you do all your multiplication and division in your dimensional analysis table, you should get 142 grams. Any questions about this problem? Cool. And this is the work for it. So just like what we were doing, a little neater. But yeah, same idea. Okay, how long in minutes would it take to electroplate a fluid with 28.3 grams of silver? This is the molar mass at a constant current of 2 amps. So this time we are given the mass and we're going to time. It's the exact opposite of the last problem, right? So in this case, we would want to start with, I guess you have a few options how you could start this problem, but I'm going to start with the mass, 28.3 grams silver. and we're doing the dimensional analysis. If we want to look over the, again, and check our balancing to check our electrons, we're saying we're electroplating a fluid with the constant using. So if we're going from Ag NO3 to silver, I guess in this problem, we could just assume one electron because we can only have Ag plus and going to silver. So you could do that. Yeah, I think that just works for this problem. Anyways, so we're going to start with 28.3 grams. And we're going to do the molar mass to get it to moles. 107.87 grams per 1 mole. Then, after we get to moles of silver, so I'm going to label moles of silver. We can go to moles of electrons. For every 1 mole of silver, we get 1 mole of electrons. And again, because AgNO3 is dissociable, we would just get, in a solution, Ag plus aqueous plus an electron yields Ag solid. Right? So AgNO3 in a solution, we could say that's aqueous, right? And so we know Ag plus and NO3 minus, that would be the ion it dissociates into. We don't really care about NO3 minus, it's kind of tertiary to this problem. So you could just write plus an electron. Yeah, basically, right? It doesn't really affect this problem. It doesn't change the time it takes to electroplate. Remember, electroplating also has to do with electrolysis. And something they always tell you with electrolysis is that the compound is molten. You guys remember what molten means? Yeah, so that's kind of where this idea comes from for this problem. Does that make sense, like how I'm finding this? For the electron? Yeah, is that making more sense? Me, Mom? Okay, cool. So now we can convert that electron using Faraday's conversion factor, 96.485 coulombs per that one electron, right? Oh, I wrote 6, 5. That was a typo. There, correction. And then we're saying for every 1 mole of electron, because we know this is a coulomb, so we could say we have 2 coulombs per second, right? Because 2 amps per 1 second. Since again, that's another conversion factor for amps. 2 coulombs per 1 second. And then we want to convert it to minutes this time. So we can't leave it at seconds, even though that is a time unit. The problem specifically asks for minutes. So we could say there are 60 seconds in 1 minute to finally get to the minutes unit. And if you look at everything else should cancel. So we got mole of Ag, the grams of silver, the moles of electrons, the coulombs, the seconds. So the only units we have left is the minutes. So we did everything correct, and we end up getting 211 minutes, 211 minutes. Any questions about this one? Cool. I think we have one electroplating problem. So this is the work for it. You can tell that it's written a little differently in a different order. There are different ways to write the dimensional analysis. I guess as long as all the units cancel out, it's the most important part. You know, you actually set it up right. But yeah, you still get the same answer no matter how you set it up, as long as your units cancel. So another one on electroplating. Chromium often is electroplated on other metals and even plastics to produce a shiny metallic appearance. How many grams of chromium? So this is our conversion, our molar mass, which is a conversion factor, would plate out from a solution of this when 10 amps of current are passed through the electrolytic cell for 5.36 hours. So for this problem, we're looking for grams again. So it's like the first one we did, right? And let's see what's going on here. So for this problem, again, assume that it's molten and that it dissolves, the NO3 being like not important for this problem. A spectator, you can write it. Yields chromium solid, like that. And so we're going to be working with 3 electrons. And then we can set up our dimensional analysis table again. And so this time, again, I'm going to start with the amps, which I'm going to convert to the coulombs per second. So we have 10 amps. So we also have 10 coulombs per second, right? So 10 coulombs, 1 second. We want to cancel out the second. We're going to say we have 3,600 seconds in 1 hour. And we know we are doing this for a duration of 5.36 hours. 5.36 hours. So now our overtime units cancel. We have our seconds canceling here, and we have our hours canceling here. So now we have to deal with this coulombs and then to mass, right? So we know we have 96,485 coulombs released per 1 mole of electron. One mole electron. Well, we know we have 3 moles of electrons for a specific problem. So then we finally can say we cancel out these, the coulombs, and then the moles of electrons. And we say we have 3 moles of electrons for 1 mole, for every 1 mole of chromium, right? And when we get to moles of chromium, we can use our molar mass. So every 1 mole of chromium has 51.996 grams. questions about this layout? Is everyone still there? Cool. 34.7 grams. Just making sure when it gets quiet, I'm like, it's getting kind of late. Are people sleeping now? Okay, yeah, I already asked if there are questions. I guess not. We've done a lot of these problems, so I see why you guys are tired of them. Yeah, but there are probably one of the more mathy parts of this chapters of this, yeah. So I guess that's why we put a lot more practice in this review for it. But luckily we got, well, this is the right answer, the solution. Are there any problems on aqueous electrolysis? Well, the problems we are working with, it has to do with electrolysis, like electroplating. Do you mean like what type of problems do you mean? Conceptually, I don't think we have anything. I think, I don't know if your textbook has other problems for it. I feel like electrolysis is mostly tested through like electroplating questions. And then maybe on how it like differs from galvanic cells. We could talk about that a bit if you like, how like kind of like what the picture he showed you, like how galvanic cells are different from electrolytic cells. Honestly, kind of the opposite in ways, with like the cathode and anode having the opposite sign. Is that some stuff you want to cover? Okay. Yeah, maybe at the end I could like draw out both of it and we could talk about it a little bit. Cool. So right now, I guess we're going to balance a basic solution, right? So this is I'm reconnecting. Can you guys hear me? Can you guys hear me? I think I was reconnecting for a second there. Okay, cool. So when we balance stuff, we have to split them into two individual reactions. So I'm going to put the one with manganese over here. And the one with iodine over here. So what's the first step we have to take when we're balancing? Even before the oxygen, we have to balance non-oxygen and hydrogen. So in the iodine, we have 2 on the right side, but only 1 on the left side. I want to add a 2. The manganese have the same amounts, so we're good on that. So let's do the one on the left first, actually. So and then after we balance the non-oxygen and hydrogen ones, we're going to balance the oxygens by adding water, right? So which side should we add the water to? The left or right? The right? I agree. How many should we add? Exactly. Now, how do we balance the hydrogens? Where do they go and how many should we add? Yep. And then if I was going to add the electrons next, where do the electrons go? So let's look. We have a no charge on the right side, but we have a 4 plus charge minus a 1 charge, right? And so then we add 3 electrons. So we have 3 plus, but 0 on the right side. What I like when you have multiple charges on one side of the equation, I first like total up my charges and then I write it over the equation, just so I can like visualize what my total charge is. Because sometimes you have the hydrogens and you have the original compound with charge, then you have the other side with charge. So I kind of like to write it out. So what's the next step since we're doing a basic solution? Yeah, I agree with your work, Caleb. You are correct. So yeah, the oxygen. How much oxygen? I'm gonna do 4. I'm trying to cancel out the H plus. And you add it to both sides so we don't affect the balancing. So it's just like adding 1 when we used to do that in like math problems, but we like add it in a form of a different number. So now we can take these 4 hydroxides and 4 H pluses, count them to make H2O. But we still have hydroxide in solution on the other side, so it's still overall a basic solution. Okay, cool. And now, is there anything else we have left to do for this side before we go down to the right side? Yeah, we have 2 over here, but 2 H2O here. Cancel this one and just put 2 over here, right? Any questions on this side? No? Okay, so what do we do on the iodine side? Do we have to do the adding water, adding H plus? Do we have to do any of that? Adding hydroxide? Yes. We don't have any oxygen hydrogens, we don't have to. So we have 2 I minus. So how many electrons? Electrons? Yeah, I agree. 2 electrons. Cool. So we have 2 electrons on this side, 3 electrons on this side. What do we do to make it equal? So we do that by multiplying, right? So we're going to multiply there and by 2 here. Cool, cool. So the last part is just adding it all up. So let me really quickly write it out. So we got 6 electrons on this side, plus we got 4, 2 times 4. 2 times 4? No, we got 2 waters on this side. So it'd be 4 H2O. Okay, cool. My work is messy. It's hard to read. Then we got 2 MnO4 minus plus 3 yields 3I2 plus 6 electrons plus 2 MnO2 plus 8 OH minus. And then lastly, we can cancel out these electrons. You don't have to write them if you know they're going to cancel. I'm just writing them to show you guys that they cancel, kind of visually. Oh, and I think I forgot to write the 2 over here. Okay. Any questions? Cool. Next one. So this is the solution. It's exactly what we got, so. And this one is balancing in acidic solution. So it's a little simpler. I prefer the acidic ones because I like the long-winded solutions. I actually like balancing. I find it fun. So first we split. So I'm going to put the iron one on this side. Fe2 plus, so yields. Yeah. I also find it really satisfying how it all like fits together. Like it all always works out, no matter like, I don't know, no matter what. It all comes together in a nice balanced package. Okay. So now that it's written out, let's start with the left side first. What do we do for the left side? Do we need to do anything except balance the charges? Yeah. So where do we put the electrons? Or electron? Yeah, add 1 electron to the right. Exactly. Cool. Now we have equal amounts of charge on both sides. Now to the left. So the first thing you might see, what's the first thing you might want to do for this problem, for the right side? Yeah, balance that chromium. We got that 2 over here. So we gotta add that 2 over here. Next thing. Seven waters. It's a lot of water. You won't go thirsty. How many H pluses then? 14. And lastly, what do we do? So we got 14 plus, and then we got 2 minus. So overall, we got a 12 plus on this side. And then here, if we look at a 6 plus, right? So how many electrons do we want to add? Yeah, 6 electrons to the left. Your balancing looks a little off to me, Caleb. So let's see. We have 6 electrons. So how much would we want to multiply iron by? 6. Yeah. I think that's where you messed up, Caleb. I think you probably multiplied by 9. Is that what you did? Gotcha. Yeah, be careful with the charges. There's a lot going on with the chromium one. So I would like add them up individually first. Okay, so once we multiply this, and we don't have to multiply the right side, thankfully, so that would take a while. We can just add up There's a bug on my screen. Okay, sorry. I don't like bugs. Anyways, we could just add up everything and get a full balance reaction. So that would be 2, or not 2, what am I saying? 6 Fe2 plus 6 electrons plus 14 H plus the chromium thing. 7, 2 minus yields 6 Fe3 plus 6 electrons plus 2 chromium 3 plus 7 H2O. Yeah, that should be your full balanced one. Any questions? Oh wait, no, my bad. After we cancel out the electrons, now it's your full L. Any questions? Cool. And here's the solution again. Let's see. So how do we do this problem? Calculate the standard free energy change for the following reaction. At 25, what are we looking for? What formula? So not exactly nursed. Yeah, it's going to be the negative NF E cell. I think nurse is the one where it's the E cell of the non-standard equal to the E cell standard minus NF, not NF, over minus RT over NF, ln Q. That's the nurse one. Okay, so this is the formula we're going for. They tell us that this is the formula, so we have to figure out the N. So the N here, what might that be? Let's see. We have to split it and check, I guess, for this problem. So if we were to split this, into gold, yields gold ion. Since we have a 6 plus charge here and a 0 there, it would be 6 electrons. And we know this is a balanced one, right? So we don't have to check the other side. It's already balanced for us. This is a balanced version of it because we got these coefficients. You guys see what I'm saying about the how I'm finding the N here? Okay, cool. So we got minus 6, and then we got the Faraday's constant, so 9, 6, 4, 8, 5. So lastly, we have to find the E cell. So that we don't have to go and flip back. I'm going to tell you the one of the cathode is. Cathode is equal to the negative 2.87 volts. And then the anode is equal to 1.5 volts. So knowing that, what do we get for our total E cell? Yeah, it's going to be negative 4.37. We have to do cathode minus this one, anode. And so let's take this and multiply it up here. And doing that, we should get that it's equal to 2.53 times 10 raised to the third. So is this spontaneous or non-spontaneous? Yeah, it's going to be non-spontaneous. And before doing the delta G calculation, you could look at your E cell and figure that out because we got a negative E cell, right? And the delta G is always going to be positive when E cell is negative. They're opposite of each other. Any questions on this one? So this is the work for it. Basically what we did, see the E cell calculation, the formula, and then the plugging in. So what would happen to a Galvanic cell without a salt bridge? Any guesses? Yeah, it would start. The thing is, initially you still have like a start with it, just will eventually stop. Because what ends up happening is you have these two beakers, right? And then this side, we're going to say our cathode, positive side, this side's the anode. And then we're going to draw it without a salt bridge. So I'm not going to draw the salt bridge in. So we know that the flow of electrons happens towards the cathode, right? Because that's where we're being produced. So what happens is, the answer to the previous question was 2.53 times 10 to the third. Yeah, no problem. So for this problem, what happens is as your electrons flow from the anode to the cathode, we're going to have an accumulation of that charge so that your cathode eventually becomes negative, right? Because if you keep getting electrons to it, eventually the reduction is just going to be completely negative without a salt bridge to balance it out. And then your cathode losing, not your cathode, your anode losing all those electrons is going to end up becoming positive, right? So all its negativity is leaving. And therefore, you're going to have this like polarization, but nothing to replenish it. And so the reaction can't continue. The anode no longer can lose it anymore, the electrons. And it's the reaction stops. So you can still see an initial reaction, it just will stop without the salt bridge. So the salt bridge is very, very, very important. And the explanation I have down here is that the anode compartment would become positively charged and then the cathode compartment would become negatively charged. Thus the charge imbalance causing the electron reaction to come to a halt. Any questions? It basically allows the galvanic cell to constantly replenish its loss of charge so that it could continue going in that cycle. And here's another conceptual one. As a galvanic cell reaction proceeds, does the cathode electrode gain mass, lose mass, or stay the same in mass? And I see Caleb's already said gain mass. How come? So I think because the electrons move towards cathode, right? Yeah, and then you have that reduction, right? We have a reduction occurring at the cathode. It means that, let's say we have copper 2 plus in solution, and that electrode has copper, right? What happens is that the electrons cause the reduction of that copper 2 plus into the product of copper solid, and so we have a gain in mass, right? Exactly, right? Because we have an oxidation occurring. So at the anode, what's happening is we have zinc 2 plus in solution. So we have zinc 2 plus solution, and we got a zinc electrode. So what's happening here is that we're being oxidized. So that zinc, when the electrons leave it, is turning into that zinc 2 plus. So the concentration of zinc 2 plus in the beaker increases, but our electrode is losing mass. Does that make sense? So be careful also what the question asks for. So if they're asking a conceptual question, be careful if it like talks about the electrode, the concentration of the solution in the beaker, because those are two different things. The electrode is the thing attached. So the wire, it's going to be the solid. The thing in solution is going to be your ion. So make sure you differentiate between those two and read carefully for that. So someone asked in an electrolytic cell, does the cathode gain mass as well? So let's look at the cathode. So an electrolytic cell, a picture like this. And we have a cathode over here, and this cathode this time is going to be negative, right? Because it's opposite. And then we have an anode over here. I'm going to label it A. This is going to be C. This is going to be positive this time. Now we're going to have positive ions flow this way, negative ions flow this way as a point of attraction. And so over here, if we're having positive ions being attracted to it, I'm not sure if it works the same way. Let me see. So for an electrolytic cell, because the way it's structured is a little differently too. So we still have the electrons flowing towards, right, the cathode, right? So we still have those electrons flowing over here. So if electrons flow over here, getting a lot of notifications at the same time. My computer is lagging. Okay. So if electrons flow over on this side, right? So we're gonna see that. I guess, yeah, I would think so. I think it occurs that way. It works a little differently though, so I'm not 100% sure. It's still completely applies, but I would assume, even though, because it's still the electrons go that way, and so what ends up happening is the negative gets kicked off, right? So I would think it's the opposite, honestly. But you might want to check with someone just to confirm. Any questions about anything? I believe this is the last problem. So no more left to go through. Yeah, no problem. Go the rest of your studying. Good luck on your exam and then your final. You guys got this. Yeah, slide 45 is just the answer. So it says gains mass. The reason the electrode in the cathode causes the reduction of the positive ion in solution to the solid product. Have a good one.